Okay, I got a request to look at the solution for this question that asks for the second derivatives of the function x to the power of y, where x and y are independent variables. So for f sub x, we keep y constant. So what this would look like if you wanted to rewrite the function with any constant for y, I would say f of x equals, let's let y be 3. I'm just going to make any number, x to the power of 3. When you take the derivative of x to the power of 3, you get 3 times x to the power of 2. Now, when we do this for f sub x, take the derivative of x to the power of y, the y is going to come down, and we have x to the power of y minus 1. Now, if we wanted the second derivative with respect to x, so I'm taking f double prime of x over here. So the 3 is still there. 3 is in front. We take the derivative of x to the power of 2. The 2 comes down, x to the power of 1. So that's what I'll do here. I'm going to take the second x derivative, fxx. I'm going to get the y minus 1 comes down, and we'll have x to the power of y minus 2. Okay, so that's one of the second derivatives. Now we'll go from f sub x to f sub xy. Take the y derivative of f sub x. Now when we do that, so our function is f sub x equals y times x to the power of y minus 1. We take the derivative with respect to y, we need a product rule. We have an a, we have a b. We're going to have a times b sub y plus b times a sub y, for a and b defined here. So that's going to be a, y, times the derivative of x to the power of y minus 1. But we have to be careful. We're taking a y derivative of x to the power of y minus 1. So for fxy, x to the power of y minus 1 looks like 5 to the power of y minus 1. We're replacing x with a constant now. We're doing a y derivative. So if you take the derivative of 5 to the power of y minus 1, we're going to have 5 to the power of y minus 1 times the ln of the base, ln 5, times the derivative of y minus 1, which is 1. So that's an exponential derivative. But we don't have a 5, we have an x. So it'll be x to the power of y minus 1 times the ln of x. That's the first part of the product rule, plus the second part of the product rule, b times a prime. b is x to the y minus 1, and then multiply by the derivative of y. Derivative of y is 1. So I can rewrite that as y x to the y minus 1 times the ln of x plus x to the y minus 1. And then you can common factor x to the y minus 1 out, and you have y times the ln of x plus 1 as a simplified form. Almost done. We need the f double y derivative. So I'm going to rewrite the function. X comma y is x to the y. For the y derivative, x is constant, so this looks like 5 to the y. When you take the derivative of 5 to the y, you get 5 to the y, except it's not going to be a 5, it's going to be an x to the y, times the ln of the base, so the ln of x, times the derivative of y, which is 1. So the regular exponential derivative formula. We're going to do it again. for the double y derivative, fyy. So ln of x is a constant. It's going to wait outside. It's not going to participate. It's going to be multiplied by the derivative of x to the y. Derivative of x to the y is x to the y times ln of x times 1, multiplied by the ln of x, the constant that was waiting outside. So we can rewrite that as x to the y times the ln of x all squared. We have a ln of x times ln of x. Okay, and that's fully simplified. Now, another way of doing this is you could have done f sub y first and then taken the x derivative. You would have had a product rule. And the derivative of, so we would have a times the derivative of b with respect to x. Derivative of ln of x is 1 over x. We have x to the y over x, which is x to the power of y minus 1. So we get that term. And then the other part of the product rule, ln of x multiplied by the derivative of x to the y with respect to x. So the y would come down, and we would have x to the power of y minus 1 multiplied by ln of x, and that's that term. So both methods will result in the same outcome. Just another way of saying that fxy is always fyx. The mixed partials calculated in either order will always be the same.